This is day 27, same binary tree. I think this is like the third binary tree problem we've done. And it is quite similar in nature. All of the binary tree stuff we've looked at so far has been a recursive solution, and we'll keep talking about it. Most tree problems boil down to something recursive, so we'll get to it again here. Okay, so here's our problem prompt. It says, given the roots of two binary trees, P and Q, we want to return true if the trees are equivalent to each other, and otherwise, so if they're not equivalent, we'll return false. And they clarify for us here that two binary trees are considered equivalent if they share the exact same structure and all of the nodes have the same values. Okay, so for example here, 1, 2, 3 being this tree here, 1 the root, and then 2 the left child, 3 the right child. Exactly the same as this one, 1 the root, 2 the left child, 3 the right child. And we return true, which hopefully is somewhat obvious here. Okay, now by contrast, example 2 here, we've got the same values in the nodes here. So we've got a 4 node and a 7 node. But notice that in one of these scenarios, the 7 is the left child of 4, and the other one, the 7, is the right child of 4. And we would consider these distinct trees. They're not equivalent to each other, so we return false. Okay, similar vibe for this one. Same structure here, but the values are reversed. There's lots of ways we can think about this, but in short, the left child of the first root is 2, or a node with value 2, and then the left child of the right node there, or the right tree, is of value 3, and so we can return false. And I wish they had given one more scenario here, which is, for example, if we had one, well, let's go over here. In this example, if we removed this 3 child, then the structure is different. Oh, maybe. Is it fuzzy? Staticky? I am doing nothing different than usual. Oh, is it usually like this? Man, okay, let me see. Let me grab some headphones and see if I can change the situation here. Me when I'm old, me when I'm unk. Exactly. Input device. Okay, is this better? Am I even coming through anymore? Yes, is it better? Or... Okay, great, I'm glad. I'm gonna hope... You know what, I've never listened to the audio on the recordings. I hope the audio on the recordings is okay. Because I just use the same settings for that. Anyways, okay, so... last scenario that they don't cover in the examples here that I'd like to cover is if we're missing a node entirely, different structure, right? So a scenario where we have a node in that place on one tree, but we don't have a node in that place on the other tree, that would be considered not the same tree, right? We'd consider them distinct from each other. Okay, and that covers most of the scenarios. Let's take a look at the constraints real quick. So the number of nodes in both trees is between 0 and 100 inclusive, so we can have no nodes. We'll have up to 100 nodes, which either way, not a huge deal. We have to deal with however many nodes there are. And then the node values, once again, we're not going to manipulate those really, but we're kind of guaranteed that they're manageable numbers. They're not going to be, of extreme values that make it difficult to work with them. So yeah, all right. So again, same binary tree here. All we're trying to figure out is it the same tree, right? So let's do a little bit of digging on this. Let's start digging in our butts a little bit here. So like we talked about last time with the maximum depth problem, and also actually the first time we did a tree problem, which was invert binary tree, what we're effectively asking with trees is, what is a subproblem that we could solve for each node that would let us kind of put a bunch of small pieces together to make the final answer, right? This is something that would that would let us. Normally, this job pays a large salary Large celery. Okay, so again, we're trying to figure out what is the sub-problem that we can solve for each node. That would let us kind of accumulate a bunch of smaller answers to create the entire answer for the problem from the root. This is true for, trees generally will follow this pattern if we're doing like a depth first type solution, but also just recursion in general, right? The whole goal is to be able to solve small subproblems that are easy to solve and then figure out how to construct them into a complete answer. Okay, so we'll do a simpler tree here because there's quite a bit to like consider, and then we'll actually cover some of the examples as well. So our example tree that was the same tree, and then we'll try and break it so that it's not the same tree and see how we can detect those things, was 1, 2, 3. So quite straightforward here. Okay, and then we'll create an identical tree over here. So let me copy this and then paste this. Wow, I can't believe you deleted that comment, because say that with your chest. You're not even going to be here next semester. Anyways, so 1, 2, 3, 1, 2, 3, right? Exact same tree, literally copied and pasted it. So if we can figure out basically how do we answer this question for a single node, then we've actually kind of answered the whole problem. And so if you're comparing two nodes to each other, the first thing that we need to figure out here is just, do these two nodes have the same value, right? So the value over here is 1, value over here is 1, checks out, right? Quick and easy way that we could break this, and we would immediately, hello? Hello? Am I crazy? Why can't I erase? Okay, I don't know what's going on there. Hello? Yeah, okay, well anyways, let's say we overwrote this with a 2 here. This would immediately confirm to us, regardless of what's going on with the children, that these are not the same tree, right? So value comparison from one node to its matching node is going to automatically, if it's not equal, allow us to immediately say, hey, these are not the same tree, right? We don't need to do any further analysis. And so in terms of recursion, that's definitely going to be a base case, is if we say, hey, we don't need any further recursion to immediately say these are not the same tree, right? Okay, so that value comparison is something we want to consider. Assuming that the value comparison works for the immediate node that we're looking at, now we have to ask ourselves, well, does this hold for the entire left subtree? And then also, does it hold for the entire right subtree, right? And so this is sort of the strength of recursion, is we can say, hey, you know what, I'm going to sort of assume that I can do this for every node individually. Now I just have to make sure that I can actually call the function, right, the same way, but using a different part of the problem. In this case, the left node, which we would consider a root of its own subtree, and the right node, which we would consider the root of its own subtree, right? Okay, so again, let's think about some ways. So we would consider, we can continue this. So now for the oranges, we would say, hey, let's compare these two. For the oranges, we can say, hey, let's compare these guys because we called them from the same place. If we get here, we know that the parent node, right, to this node had already been considered equivalent. Now we can do the same thing. We can say, hey, the value is 2. The value is 2. So far, there's nothing to make us think these are not the same tree, right? Looks good so far. And actually, let me erase this because that's actually not the next thing we're going to do. Because for these nodes, now we need to ask the same question. Hey, does the left node and the right node have the same structure, the same values, right? So another scenario we've got to consider here that isn't really directly represented in the diagram is if we hit none at the same time. This is actually a good sign, right? Because this means that one node does not have a left child and the other node also does not have a left child, which is actually, that would confirm that so far it is the same structure, right? Okay, and this is another one of our base cases. We don't need to go any further in terms of recursion if we hit none at the same time, because there is nowhere further to go, right? So that's another one of our base cases that is sort of a good, a happy base case, shall we say, which is when we hit none at the same time. Okay, and so at this point, we've confirmed that the nodes, right, 2 and 2 have the same value. We've confirmed that the entire left subtree has the same structure. They're equivalent, right? And now we need to figure out, hey, does the entire right subtree have the same structure? And this is the same base case. We hit none at the same time on both of these. And we return, hey, looks good so far. So based on what we know so far, this is true, right? Okay, and now the entire left subtree of the root is done. We'll go over here and say, hey, let's go ahead and try it with the right subtree, right? So same scenario, we say, hey, 3 and 3 are the same. So again, no reason to think that they're not equivalent so far. And now we say, well, I also need to know if your left subtree and your left subtree are the same. And they are. Are your right subtree and your right subtree the same? Yes, they are. And at this point, we've confirmed the entire right subtree is equivalent, and that means we're done, right? So basically for every node, all we're saying is, are the values the same? Are the left subtrees the same? And are the right subtrees the same, right? And if we do it in that order, which we should at least do the self node first. Again, we call that a pre-order traversal. It means handle the self and then handle the children, right? That's the best way to do it in this case because, again, if we hit that, if we know that the values are not the same, we can immediately exit. We don't want to do extra work, right? We want to exit as soon as possible. So it makes sense to do a pre-order traversal here. It'll work regardless, but pre-order does make a lot of sense here. Okay, so again, what are some other scenarios that could break this? We already considered what if the values are different from each other. Another thing we have to consider, so pretty easy way to make this broken here, is what if, for example, this guy actually did have a left child, and it doesn't really matter what the value is, maybe it has a value of like even 0. Doesn't really matter. In that case, when we got to this purple step right here, we would say, hey, let's confirm that the left subtrees are equivalent. We would get none here, but we would get something over here. In this case, there is a value, right? This is another scenario where structurally we can say, hey, they're not the same tree. This is a failure-based case where we can say we already know immediately at this point. We don't need to look further. The structure was wrong at one point, which means they cannot be the same tree, right? Okay, and it could be the other way around. It could be that there is a node on the left or on the first tree, and there is not a node on the right tree. Those are sort of equivalent, just backwards logic, Okay, so let's just write down some of the things we figured out about some success-based cases. And really, actually, the only success-based case we need to consider here is if we have none and none. This means I can stop. I don't need to look any further, right? All the other successes, or the things we consider successes, like the red part right here, this is a good thing so far, but we have more recursion to do to fully answer the question, right? So none and none is a great place for us to be in. Some failure-based cases. This would be if we have none and node, or node and none, or one value does not equal the other value, right? These are all places where we can say immediately, hey, this cannot be the same tree. We can immediately return false. And then in terms of how to combine these, it makes sense for us to use an and here, because if we hit any of the failure-based cases, we want to return false, right? And that's exactly what and does, right? Or would mean if anything works, then we can overall say yes or return true. And would tell us you need to make sure that all of the scenarios work out properly, right? Okay, and all that's left here is to kind of assemble these guys into some recursive statements. But again, the subproblem that we're solving here is if you can compare the two nodes you're looking at, and then confirm that the left subtree and the right subtree are also equivalent, you can repeat that for every node in the tree, and our base cases look like these guys here, where we can immediately conclude true or false. All right, enough talking. This is actually a fairly straightforward problem, so I don't want to spend too long on it. But let's see if we can recurse a bit. As usual, any questions, please let me know, but let's tackle the code here. Okay, so lots of base cases for us to consider. Let me actually split screen this. I'll close that and then slide this over. Hello. Okay. All right, so let's actually code up our base cases first. So we have P and Q, which initially are the roots of the two trees, but if we call this again, we can choose whatever nodes we wish to compare with P and Q. Okay, so if so our only success base case is if it's none and none. So if not P and not Q, this is great. We want to return true. Okay, and then here's the other scenarios. We can say if not P and Q, or P and not Q. So this is, we have a node in one tree, but we don't have the node in the other tree. We can immediately return false. And then finally, if p.val does not equal q.val, we can return false. And I have structured this way on purpose. We want to do all of our null checking ahead of time, right? We want to say, hey, let's make sure that we can actually call .val on the thing that we're using. So at this point, we know that they're not both none, because if that were the case, we would have returned true. And we know at this point also that neither of them is none, because if either of them was none, we wouldn't be able to get to this part. Anyways, it would also be fine to say right here, or p.val does not equal q.val. I just think it's nice structurally to sort of separate these, like rather than having a million things all at once that all return false. This is, you know, performatively equivalent to just checking these and then checking this. It's what we would have done anyways. Yeah, sorry, I shouldn't have said it that way because I knew you were going to say that. From a performance perspective, this is the same, right? And I think it's a little bit clearer, and even, as I am so often reminded, we can comment this a little bit more clearly too. Okay, so I don't know if we need to actually, because like these are pretty self-explanatory. So they're both none. One is none, the other is not. The values are not the same, right? These don't necessarily need comments. But I think it is nice to split them like this. Okay, so those are all of our base cases. Now, assuming we didn't fail, and we also didn't immediately know that it was the same structure because they were both none, what are we going to do? Well, now we know that we have two nodes with equal value. So we haven't failed yet, is a way you can think about this. But what do we need to check next? Well, it's not enough that the nodes themselves compare well. We also need, again, for the left and the right subtrees to do the same thing. So we know that we're not dealing with nuns, so we don't have to do any null checking here because we handled that up here. We can just say return self.isSameTree p.left and q.left. So now, again, we can summarize this as determine if the left subtrees are equivalent, and self.isSameTree p.right, q.right. And again, summarize that as tell me if the right subtrees are equivalent. And again, we're combining that with an and, because if one of them fails, so for example, in this one, if the left tree fails, we won't even look at the right tree. We can just stop immediately and return either true or false. Okay, so if you think about this from the perspective of the root node, if these are the same tree, we're not going to hit this. Well, either we can return true if there's no nodes at all, but assuming there are nodes, we will say, hey, the values are equal to each other. We get here. And now just go ahead and confirm to me that the whole left subtree is equivalent and the whole right subtree is equivalent. Okay. I think that's it. Let's give it a run. Feels good, man. And feels good, man. Sweet. Body T, exactly. Exactly. You guys know what I mean when I say like two girls, two blonde girls just looking at each other going, exactly, exactly. That's how I feel sometimes with myself. Um, oh. Okay, anyways, that's today's problem. Again, we're going to be doing recursion quite a bit. We are going to use that as our default approach for depth first search. And occasionally we'll need breadth first search. That looks a little different. We won't have to recurse, but same overall idea of like solving a subproblem and then letting that kind of proliferate through the rest of the tree. All right. Any questions? Again, this was same binary tree, if you were wondering. Anything interesting happen? No, Hailu is just depressed. And y'all did it to him, let me tell you. I know. Okay, we'll call it there though. I'm just going to go ahead and end the recording. But if y'all have questions, let me know.